AQA, A-level physics, electrical potential. This chunk of the specification. Now, if you understand gravitational potential, this should be easy, he says. Before we look at electric fields, potential in electric fields, let's go way back to when we did electricity and electrical circuits. Now, potential, the potential at a point is the amount of electrical potential energy 1 coulomb of charge would have at that point. So, you know, here's my little friend. I waffled on about him a long time ago. Colin the Coulomb, and how much energy has Colin the Coulomb got? And when he's at this point here, Colin's got 6 joules of energy, yeah, electrical potential energy. And then he comes round here and he goes through this resistor, and in this resistor he's going to lose, and I've just realized, yeah, no, we're okay. He's going to lose 2 joules, isn't he? Yeah. And then he goes through this resistor here and he's going to lose 4 joules. Yeah. Why? Because I know that we're going to have 2 volts across there, and a volt is a joule per coulomb. We're going to have 4 volts across there. A volt is a joule per coulomb. So basically Colin's got 6 joules at that point. He's got 4 joules at that point. Okay. And he's got 0 joules at that point. He's absolutely knackered. And he gets back, he crawls all the way. Well, he doesn't crawl because he doesn't slow down, but he gets back to the power supply and he fills up with petrol again, and he's round again. So the potential at a point is how much potential energy a coulomb has at that point, and then the potential difference is the difference in potential between 2 points. Okay, that's what a messy diagram. So the energy transferred between 2 points, W equals Q delta V. Delta V is your potential difference. Now, this is our uniform field. So 2 metal plates, and we have a positive plate and we have a negative plate. My power supply, I'm using 1000 volts. Now, our negative terminal, we usually say our negative terminal is our 0 of potential. Usually, not always, we say that the negative terminal is earthed. And that means that a coulomb there has no potential energy. So we take our negative terminal as being 0, that's 0 volts. The potential difference between that and the positive plate is 1000 volts, because we've got a 1000 volt power supply. And then this is how the potential varies between the plates. These are my equipotentials. And notice that the equipotentials are evenly spaced because it's a uniform field. The equipotentials are evenly spaced. Yeah. The energy transferred between 2 points is Q delta V. If I wanted to know how much work I would have to do to take a charge from there to there, yeah, it would be Q delta V. Or if I put a positive charge there and let's say it gained kinetic energy and went to there, okay, how much energy would it gain? Q delta V. Equipotential surfaces are evenly spaced in a uniform field. If we did a graph of potential against distance, it would be a straight line. In this particular case, it would go from 1000 volts down to 0, and it would go down uniformly. So the gradient of my potential hill is uniform. My field strength is uniform. It's a uniform field. And my potential gradient is V over D. How do you get gradient? Well, it's V over D. That's the gradient. Hopefully everything's clicking, it's coming together, it's making sense. Now, this is a non-uniform field. This is a field due to a positively charged sphere. So imagine this is like a metal dome, which is positively charged. We've already talked about the field lines. Now, look at the equipotentials here. So if the potential at the surface is 1,000 volts, then look at these equipotentials. 800 volts is there, 600 volts is there, 400 volts is there, and notice that, well, the zero of potential will be at infinity, which is way, way over there somewhere. That's where our zero potential is, not the negative terminal, because there isn't one. So just as with gravitational fields, zero of potential is at infinity. The potential at a point is the work needed to take 1 coulomb from infinity to that point. If I had to take a charge of 1 coulomb from infinity, from very far away, closer to the sphere, I would have to do work. And the work needed per coulomb is the potential at that point. It's the electrical potential energy per coulomb at that point. For a positive charge, potential is positive. For a negative charge, potential is negative. So a positive charge creates what we call a potential hill. Remember that when we did gravitational fields, we talked about a potential well. Yeah, there's a potential well. Here, in this case, we have what we call a potential hill. Yeah, you'd have to do work to get closer. With a potential well, you have to do work to escape. With a potential hill, you have to do work to get closer, because it's a repulsive field. With a repulsive field, you have to do work. It's like squashing a spring. You have to do work to get closer. Notice the equipotential surfaces get further apart. Why? Because the field gets weaker. Because my potential gradient gets smaller. Yes? So to travel the same distance, so rather for the same amount of work, you could travel a bigger distance. How do we work out the potential in a radial field? It's V is KQ over R. K is 1 over 4 pi epsilon naught, which is about 9 times 10 to the 9. So V is KQ over R for a radial field. Let's just focus on what you need to know. We have a charge Q. Q is creating an electric field. If VA is the potential at that point A, okay, VB would be the potential at that point B. The potential at infinity, a long, 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 long way away, is 0. Yeah. If we wanted to work out how much work would have to do to get from B to A, or how much energy is transferred between A and B, then it's Q. Well, the potential energy of a charge Q is QVA. The potential energy of a charge Q at B would be QVB. How much work would you have to do to get from A to B, or how much energy would be transferred, would be Q delta V, which brings us all the way back to this equation, which I keep repeating, W equals Q delta V. Can you do this question? An alpha particle has 7 MeVs of kinetic energy. It approaches a gold nucleus head on. What energy transfer will take place? How close will it get? Do you think you could have a go at that? I'll show you the answer in 3, 2, 1. Okay, so kinetic energy goes to electrical potential energy. Kinetic energy is 7 mega electron volts, so 7 mega times little e. When my alpha particle is there, how much electrical potential energy has it got? Well, that's little q, that's the charge on the alpha, and this is the potential at that distance due to the nucleus. So at that distance from the center of the nucleus, let's go blue, at that distance from the center of the nucleus, that is the potential at that distance. So those two together is the electrical potential energy. And if you work out R, you get this, about 3 times 10 to the minus 14. That's actually called for the distance of closest approach. It's not the size of the gold nucleus, but we do know that the gold nucleus must be smaller than that. Okay, so it's good evidence that nuclei are an awful lot smaller than atoms. This should ring a few bells from the gravitational topic, if you understood that. If you've got a graph of V against R, then it's an inverse relationship, because V equals K 9 times 10 to the 9, 1 over 4 pi epsilon naught, etc., etc., KQ over R. Notice that V is positive if it's a positive charge producing the field. Notice that it's just over R. Yes, it's not over R squared. My field strength, E, is KQ over R squared. Yeah, potential is over R, field strength is over R squared. And you can see the shapes of the graphs. E goes down a lot quicker. Yes. Now, my field strength is the gradient. It's the slope, the potential gradient. Okay, so at that point there, the slope of the graph tells me the field strength. The steepness of my potential hill is equal to the field strength. If you differentiate, you all do A-level maths, don't you? If you differentiate that, you get that, don't you? Yeah, so E equals dV dr. My graph of E against R now. How do we get the potential off this graph? Well, the potential at a point would actually be, if I wanted the potential at that point there, at that value of R, it's actually the area all the way to infinity. So the area all the way to infinity tells me the potential at that point. Okay? If you imagine this is my expression for E, if I integrate that, then I get V, don't I? And when you integrate, well, it's the area under the curve, isn't it? If I want to know the potential difference, well, it's the area between those two values of R. So delta V is the area between those two values of R. Okay, so it's a very common little multi-choicey question. V against R, the slope tells you the field strength. E against R, the area tells you the potential or the difference in potential.